Okay, why don't we build our first amplifier? It's a single transistor amplifier.
Okay, yeah.
Okay, and as it'll turn out, as you know, Tom, this will work into a circuit we've already built.
Ooh.
So let's maybe put it up here. So we're going to have some VDD. We're going to go down to a resistor. Those of you that were paying attention last slide just see that we've got exactly the same thing as before. Now we're going to call this our V out.
All right.
With respect to ground. So put a little ground up there. Okay. And now we're going to feed it some V in. Again, with respect to ground. Yeah?
Looks good so far.
Okay. So let me jump right away and replace this. So we're going to have our ground plus minus V in. This is also going to be the gate. And we're going to have our G times VGS is the value of that. And we're going to have our little resistor, RD, and VDD. This is going to be our V out.
Okay, and let's just make sure that we label D and S.
Thank you, sir.
Very good.
Let me circle them. Okay, so what we've done is we've replaced that with that, and now we can analyze it.
Okay, great.
Okay, so let's think about this for a little bit. Let's not think right now too much about values of stuff or what the input looks like. But if I'm in saturation, right? If I'm in saturation, what is the value of V out? Just thinking it through, using the stuff we know.
If we're in saturation, we know that IDS, this current, is a constant value, right?
Yep, that's right.
And that current flows through RD, right?
That's right.
So there's a voltage drop across that resistor.
This equals IDS effectively, because there's nothing that can run down this way. It's all going to run down that way, right?
Okay.
Yeah, and this is going to be equal G times VGS.
That's right.
And you're saying there's going to be a little voltage across this.
Yeah, there'll be a voltage across that resistor.
So V of RD is going to be what?
Well, it's going to be the current flowing through the resistor times its resistance.
Exactly.
Perfect.
Fair. Now, what by KVL, what's V out?
Okay, so V out is going to have to be VDD minus that drop across the resistor.
That's right. And you can all at home do this because VDD is the distance between ground, and up here. And so V out must be that minus whatever this drop is.
Exactly.
That's a
perfect
KVL. So we'll do that. It's going to be VDD minus GVGS times RD. Okay, so what we see is whatever input we put on in this particular case, because Vn happens to be VGS, is going to get multiplied by the gain and times the resistor and subtracted out from VDD.
Okay.
Right? Let's look at how that looks like for a real input. Okay. Now, what could a real input be? Well, one thing that we need to be conscious of is that this thing needs to be in saturation, right?
That's right.
So I have to ensure that there's enough, that the VDS is going to be high enough that I'm on that right side of that curve.
Okay, so V out must be some minimum value, right? That keeps us in saturation.
Exactly.
It has to be above that threshold.
Yeah, and so one way to do that, or the way we're gonna do that, is we're going to have the input have a bit of a DC offset that ensures that we have enough VDS running through. Does that make sense?
Yeah, that makes sense. I mean, we want this current flowing through that's the right amount, so we always have some voltage at the output, enough to keep our model valid, right?
Yep. So we're going to have a DC voltage at the input and some little wiggle that's the function of time. And it may very well be that this thing is the signal we care about, right?
This is looking a little familiar to me already.
Yeah.
I mean, isn't this what I guess we'll come back to the microphone, but I think that's what's going on.
This is what we promised we'd tell them. This is what's inside the electrode.
All right.
But you see the reason, I want to make sure you link it to, we needed to make sure this thing was saturated, right? So if we provide a DC input, forget about the thing on the right. If we just provided the DC input, we assure that we have some constant thing on the output running through. It pushes the output out into the saturation
And that
region.
constant output current and that constant output voltage perhaps isn't interesting to us.
That's right.
Because the signal is the small AC, but we need it.
We need it. And then we're gonna have to get rid of it, but that's okay. So Let's look at a couple of, let's do some numbers. So let's pretend V in was 500 microvolts. This is just a quick exercise. And we had 40 cosine 300t microvolts, right?
So I see the DC and I see the AC in there.
That's right. And here's a little plot of what that would look like. Okay, so the input itself has to have a little bit of this DC on the wiggle superimposed. We're going to get back to that in like 30 seconds and show you how the electret does that. But if I do this, then my numbers for here, the output we calculated would be, so VDD minus G times RD times this 500 microvolt plus 40 cosine 300t. And then let's pick, oops, a little sloppy there. Let's pick some round numbers. These are close to what we did in the electret, but they're really just so the math is easy. Let's pretend VDD was 10 and RD is 1 kilo ohm. And let's pretend the G for this transistor is 10 and the units are amps over volts. Okay? If I plug all this in, I'll get that V out equals 5 volts minus 0.4 cosine of 300t volts.
Well, that's very interesting. At the output, it looks like we sort of have our DC voltage that keeps us in saturation.
Yeah.
And then an AC voltage, which is sort of like our amplified version of the input. Okay, we started with 40 microvolts and we ended with, well, looks like 400 microvolts.
Yeah, so of course the frequency didn't change. We all know about that now, right? It's a linear circuit. And hopefully I did my math and you can see that this amplified up. The DC part amplified up again, and then we have to get rid of it. Now let's go back to an electret. Let's see how we do this in an electret, and let's see how we do this in real circuits, and then we'll wrap this up.
Okay.
So in an electret, what you actually have inside the electret, that little can, is you have a thing that's pretty much a capacitor, okay? Except here's the trick. So it's a capacitor in the sense that it's got these two plates, right? But the trick is that when they're fabricated, the plates are made so that there's permanently trapped charge.
Oh,
Just
so that there's
charge
charge stuck and embedded
It'll stuck,
in this.
and it'll last forever, basically. I mean, not forever, but a long time.
And that's what's called the electret material.
Yeah.
Right? It's usually some plastic or some
Yeah,
insulator.
it's a
that'll
polymer
store the
usually, and you kind of use these tricks to kind of get some stuff stuck into it with charge.
Well, that means we have a pre-charged capacitor. Doesn't that mean
Exactly. It has a voltage. So if you're not doing anything to it, if the thing is just sitting there, that little thing has some, call it VDC. It's some voltage that's stuck across there permanently. All right? So far, so good?
Yeah, okay.
Now, before we talk about how it does sound, what also is inside the can is something like, it can vary a little bit, but something like a little FET. Okay? And then if we go out here and just sort of surround this with the circle, this is what was in your electret.
Oh, that's our can.
Well, I guess it doesn't include the ground connection. The ground is outside. But that's what's in the can.
Mm-hmm.
Okay? And we connected that to other stuff, a resistor and so on. So what do we do? What was happening? When you talk, you wiggle these two little plates. So when you wiggle them, you're adding, on top of that base, you're adding a little signal.
Oh, as you're moving the plates of the capacitor, the voltage across the plate changes a little bit.
A little bit.
A little. Tiny bit.
What does that look like? That's exactly, this, right?
Oh.
And so what happened when we connected our electret, what did we do? Remember, we had a VDD up here and we had a resistor, and then this was our output.
Oh.
That's what was going on. It was a single transistor amplifier.
So we had a large DC voltage, and then we had a little.
And why did we put the cap here?
Signal there.
Remember?
We didn't want the DC voltage to move on to the next part of our circuit. We had to filter it out.
Yeah, get rid of this. That's right. That cap got rid of that part. Now, you might wonder, not every amplifier you build is going to have a conveniently built-in DC voltage.
Yeah, it's a little strange, right? I mean, sometimes, you don't have the luxury of having an electret material. How else would you set that voltage?
So what do you think? You're an expert at this?
Well, yeah, I guess so. So one thing that I would do is I would take advantage of the fact that we have a VDD in our circuit from our battery or wherever it comes from, and just put a couple of resistors there, make a voltage divider, right?
Yeah, exactly. So a very common thing to do, I'll reproduce this thing. So this is the original thing, and here's ground, is you actually build some resistor circuit that gives you a DC point between between ground and VDD. This is call this R1 and R2. And then your signal comes in here, and then you run that to the FET.
Oh, okay. So we can set where, the DC level there by
Hmm.
picking R1 and R2. It's just a voltage divider.
Yeah, and this is called biasing. And there's lots of different tricks for biasing. This is a very simple one. You can do biasing it on not just the gate, but you can bias all sorts of parts of the transistor. And again, if you like this stuff, there's lots of fun to be had digging in deeper and looking at the wealth of transistor topologies. Now, an op amp, does an op amp have one transistor?
It does something a little more complicated than just one transistor can, but
Right. So a lot of the beauty of what's in an op amp is that by using a number of transistors, you can recapture a lot of those wonderful properties in an op amp with topologies that are a little more complicated than this. But really at the heart is stuff that like what we just looked at.
yeah, so if you're curious, you can go ahead and look at the data sheets for your op amps and see what's really inside are tons of these transistors doing all kinds of interesting types of amplification. And it's just this really colorful world of circuit engineering that can be fun to get lost in.
Absolutely.